Welcome back to ECE 442-542. We are at the review session for exam number 3, and we're getting close to the end of the semester. Obviously, we have 3 exams. This is your last midterm before the final. The process is consistent with what we've had for the first 2, just one more sheet of notes. The topics are homeworks 5 and 6 plus, meaning we maybe have a little bit more in terms of root locus sketching or PI controls that maybe weren't as emphasized on the homework, but all of that is fair game. You should look at the practice exams to get an idea for what you can expect on this exam number 3. Transient performance, how is that connected to Z-plane pole locations? Transient performance, I'm meaning settling time, percent overshoot, and time to peak. You should be able to go back and forth. If I give you performance specs, you should be able to find Z-plane pole locations. If I give you Z-plane pole locations, you should be able to tell me for a 2-pole system what that corresponds to in terms of settling time, percent overshoot, and time to peak. That's what I mean by going back and forth. You should be able to work through the design method of Ragazzini with the 4 different restrictions. You should know how to produce a proportional controller, a PI controller, and put those into a standard root locus configuration to do the root locus design for a P and PI design, and how do you sketch root loci for different pole zero patterns, and what are the properties. Let's go through some of those. And first, let's look at transient performance and Z-plane poles. And there's several different ways that you could go. You could call it a system identification problem. Maybe somebody walked up and put a step input into a system that they don't know the transfer function for. Well, if they give you this step response, you can now extract or identify that transfer function. You can now use that step response to give you the transfer function of the system. And what would you do? Now you would physically measure, and this is subjective, where some of these points are, but use your best judgment. Hopefully it's pretty clear where Y max is, but in this case, on the discrete time case, try to count the number of ticks to get you to the T max. And hopefully you can be accurate in that and not be 1 or 2 off. It makes a pretty big difference in your angle for theta sub D. Here your percent overshoot is the maximum value minus the steady state value divided by the steady state value. And time to peak is clear, Y max is clear, and the settling time, that's the one that maybe requires more subjectivity, but when it looks like it's getting close to the steady state value, you can say, okay, here's where I'm drawing the line and saying this is my 1% settling time value. You can now find the 2 poles that produce these performance behaviors, be that settling time, percent overshoot, or peak time. You can use those to find the radius and the angle of those poles, and now you can find G of Z from those 2 poles. We're assuming now a second order transfer function. If I was now using this plot to determine the transfer function, and let's say that green line actually ended up being 3, and I said this is a result of applying a unit step to the system, what's the DC gain of this particular G of Z? We know the DC gain times the unit step is the final value. What's the final value in this example? 3. That was given, or you'd read that off. And what's the unit steps magnitude? Unit. So there it's 1. And now we can say that G of Z, the transfer function evaluated where, equals what? So now to find the DC gain, we need to evaluate the transfer function at Z equal to 1. And because we're assuming, and in some exams I might say not a unit step, but a constant step of magnitude 7 or magnitude 2. Then you would put a 2 there instead of a 1 and back out the appropriate DC gain. In this case, because I'm saying that, oh, we applied a unit step, we can now say that the DC gain better be 3 for this particular case. And that's how you could then determine maybe an unknown constant in your G of Z. You found the denominator by the performance specs. Now maybe you have an alpha or some other parameter, a gamma, in the numerator. You could solve for that gamma by using the DC gain. The time to peak is 1/4, let's say that's given. Now I'm sort of going back and finding these R's and theta sub D's. Theta sub D is related to omega sub D, the damped frequency. That's omega sub dt. And we can now replace omega sub D. That's equal to theta sub D over T. So that now we have pi over theta sub D over T. And that's equal to pi T over theta sub D. So if now you know that the time to peak is 1/4, you could solve that for theta sub D. Theta sub D is now pi T over 1/4. And that's now your angle of your dominant poles. And that's obviously going to depend on the sample period, capital T. And that will be some angle, theta sub D, in radians. From this experimental result, we're saying the settling time is 1. And now the 1% settling time is related to the radius of those dominant poles. R raised to n sub s, the number of samples in that settling time. And if we measure t sub s to be 1 and somebody gives us the sample period t, we can now find the number of samples that have to occur. And then we can simply back out what this radius is from that equation. Solve it for R to obtain the dominant pole's distance from the origin in the z-plane. Now that we have R and theta sub D, we know those poles, and if somebody says, oh, assume that you have a 0 at the origin, you could put a z in the numerator, and alpha, how are we going to find alpha? That's using the DC gain, isn't it? And we would replace z with 1, so that now here, if we solved this for R, we could take the log base 10 of both sides, and we now have n sub s equaling -2. We could divide by n sub s and take the anti-log, and now we have R is equal to 10 to find R in terms of number of sample periods. That gives us R. The time to peak gave us theta sub d. We could also use the percent overshoot to give us zeta, and we have formulas, and we may have some later that show the relationship between zeta, theta sub d, and R, and percent overshoot.
So if we know n sub s, like,
if you're given the number of samples in the 1% settling time, capital N sub s, yes, you could use that to find R. And that's what this equation right here would allow you to do. If you weren't given N sub s explicitly, but found the time in seconds, settling time, and given the sample period t, now you can back out N sub s. Again, we're staying with this transient performance and z-plane poles. We did it for system identification. We can also use it to create a desired transfer function. I could now give you performance specs, and you now come up with a g of z. The other way, we had the performance behavior, and we found g of z. Now, if somebody gives you the performance or the percent overshoot, what does that make you think of in terms of shape in the z-plane? What's the percent overshoot? The red should have given it away. That's the hearts, and those correspond to these logarithmic spirals consistent with the zeta value, the damping ratio, in the z-plane. If you're given the time to peak, what shape does that give rise to in the z-plane? Do you remember? And if you don't, you need to know by Wednesday. Now we're talking angles, or theta sub d, and by the process of elimination, if somebody gives you the settling time, those are now circles, and we're dealing with R. Or in the z-plane, now we're trying to determine satisfaction simultaneously of these specifications. Settling time circles, logarithmic spirals, percent overshoot or hearts, and time to peak angles. Meaning you could be given performance specifications and come up with z deltas or a transfer function. Or maybe now you're deriving closed loop behavior from a transfer function, and you've now determined the closed loop poles. Now you've been given z delta, and now you want to find the performance specs. So there's many different ways to interrelate transient performance and z-plane poles. And there's a table that relates pairs of these to each other and formulas that allow you to go back and forth. if you're given closed loop poles, you should be able to find those in terms of a polar representation versus rectangular representation. The polar representation, you have the radius and the angle. If you know theta, if you know r, that's now these concentric circles. That allows you to derive the settling time, T sub s, because you can solve for n sub s if needed. N sub s is now this minus 2 over log base 10 of r, sort of this ceiling function on that. You take the smallest integer above some value, and that's now n sub s. If you now have theta sub d, you can determine the time to peak from that theta sub d. If somebody said, what's the peak time from this closed loop set of poles, and let's say it's second order, then you can find these z deltas, or it's the dominant. Or another scenario, which maybe we haven't derived, but you can go home and derive that if you want. If somebody gives you r and theta sub d, you can actually now find analytically the zeta value. You could do it graphically too. Once you have this plot of logarithmic spirals on the z-plane, you could sketch the radius and angle and see where that intersects these zeta lines, these logarithmic spirals. Here's a way to do it analytically. You take the natural log of the radius, square it, that's in the numerator. You take the angle in radians, square that, and add that same squared r to it, and then don't forget to take the square root. Once you have that zeta value, you can now plug it into the percent overshoot formula to calculate the percent overshoot for that fixed value of zeta. And if you want, you could generate something like this in MATLAB. You could plot that PO function as a function of the damping ratio zeta, and now you could simply read off from this. If somebody said, oh, I have a 10% overshoot, well, that's a zeta value of 0.6. I have a zeta value of 0.7, well, that's a 5% overshoot. This curve gives you that very quickly without having to plug in a lot of numbers on your calculator if you wanted to. Somebody now maybe says, oh, I have a 40% overshoot. Well, now your zeta value is about 0.28. Again, you're eyeballing this. It's a chart. Or somebody says, oh, I have a damping ratio of 0.5. Well, now you have about a 16% overshoot. If that doesn't make you feel comfortable, you can start using all of these formulas, which I hope I've typed in correctly. But that's e to the minus zeta pi over 1 minus zeta squared. That's the percent overshoot in terms of zeta. The percent overshoot, if you've measured it from a step response, you could calculate your zeta. Don't forget to take the square root of that. Or if you now have r and theta sub d, you could calculate where those intersect these logarithmic spirals in the z-plane by using the radius and angle in this bottom equation. Remembering that theta sub d is related to the damped frequency of oscillation in the analog setting by omega sub dt, where theta sub d is unit-wise radians per sample. That's this relationship between performance specifications, transient behavior, and z-plane poles. You can look at it many different ways, forwards and backwards, all around. That's the idea. Ragazzini in one screen. Well, actually, Ragazzini is really two steps. The first step is creating this desired closed-loop transfer function, T sub c of z. And on the exam, I may just ask you to go that far. Don't go any further. If I don't ask for the controller, don't give me the controller on the exam. Just give me T sub c of z. That's one of the parts that you have to be able to do. Maybe that's all I'm testing you on in that problem or that part of a problem. T sub c of z. We have four restrictions. Causality. Causality of what? Do you remember? What has to be causal? Your controller has to be physically realizable, doesn't it? So the controller has to be causal, which really puts a constraint on the pole zero excess of T sub c of z. What are you doing with the pole zero excess from restriction 1 of T sub c of z? What are you comparing it with or making sure it's at least the plant? The original system has a pole zero excess. You can't reduce that in your desired closed loop transfer function. If your original plant has a pole zero excess of 2, you can't make T sub c of z have a pole zero excess of anything less than 2. Is that clear? It has to be 2 or more. You have to have 2 more poles than finite zeros in T sub c of z. That's restriction 1. Restriction 2, if you have unstable zeros in your plant, you have to include those factors in your desired Ragazzini transfer function T sub c of z. Restriction 3, if you have unstable poles in your plant, then you have to worry about 1 minus T sub c of z, that expression vanishing at those unstable poles. And restriction 4 concerns steady state accuracy. One of those might be, you might want your DC gain to be 1 of that T sub c of z. And what does that mean if your DC gain is 1? What does that give you? Pardon? That will give you an output equal to what you put in. Is that what you said? My hearing is terrible. I apologize. So you have to speak up if I'm to try to hear you. So a DC gain of 1 says that you have 0 error due to a constant input. If you put in a 6, your output is going to go to a 6. If you what? If your system is stable. And you better design T sub c of z to have stable closed loop behavior. Your poles better be where in T sub c of z? Inside the unit circle. A lot of your homework, they were corresponding to a deadbeat behavior. They were right at the origin, but they don't have to be. They just have to be inside the unit circle. And you could, on the exam, be asked to satisfy particular performance specifications for the poles of T sub c of z. So the earlier piece now is applied to finding the denominator of T sub c of z. That's the first half of the Ragazzini design.
So for making sure that it doesn't cancel stable poles and zeros, we find the process of problem that we end up canceling, then should we just, because I don't think we ever discussed what to do in that case.
So the question was, what happens on the test if your C of Z ends up canceling unstable poles and zeros of your plant? Then you've done some errors. You've made some mistakes. Either your Restriction 2 and restriction 3, you set them up wrong or you have an algebra mistake. Restriction 2 and restriction 3 are supposed to guarantee that C of Z will not cancel any unstable poles and any poles and zeros outside the unit circle. So as a check, if you now are looking and you go, oh, wait a minute, C of Z is canceling a pole at 3.5. Whoa, that shouldn't have happened. Then I would say on the exam, I've made a mistake. Either I've calculated something wrong or something is wrong. I would admit that so that I know, oh, good, they understand that in the heat of the exam calculation, something went wrong. That's what I want you to be able to do, to tell me. Don't say, oh, I hope he doesn't notice. That's not the right response. Okay? So, restrictions 2 and 3 are designed to ensure that you're not canceling unstable poles and zeros of G of Z with your C of Z. That's the whole point of having those two restrictions. The second half of the Ragazzini design, which is really kind of the easy part, it's just algebra, is to solve for capital C of Z, the controller. And you can see now how restrictions 2 and 3 play into not allowing you to make those cancellations. T sub C, having a numerator factor with unstable zeros in it, are going to cancel the G of Z unstable zero factor so that they don't appear in C of Z. The unstable poles of G of Z are going to be canceled by the 1 minus T sub C of Z's that evaluate to 0 at those unstable locations. That's what's guaranteeing C of Z does not possess those factors. Let's look at an example. Suppose now we start with G of Z equaling Z minus 1/2 over Z times Z minus 1. And the only statement in the problem is the closed loop system has deadbeat response. And you're supposed to design this using Ragazzini. Where do we begin? Now what do? We have a plant. We're supposed to design a Ragazzini-based controller. He just gave us 4 restrictions. Shoot. Now what? You need to come up with a T sub C of Z, right? What if you said, oh, I'm just going to... Can we use that for T sub C of Z? What do we need this T sub C of Z to... So now you could... Usually you would start kind of stepping through the constraints to inform what T sub C of Z will look like. Here I just sort of plopped one on the table and said, let's examine this. Let's poke it and prod it. And how are we going to do that? Let's look at how it stands up to the restrictions. Does it satisfy restriction 1, this T sub C of Z? What is restriction 1? Causality, which really means relative to T sub C of Z, what do we need T sub C of Z to possess relative to the plant? The pole zero excess has to be at least the same, if not more, than the pole zero excess of the plant. What's the pole zero excess of the plant? 1. What's the pole zero excess of T sub C of Z? Check. Move on. Yes.
So you greater than or equal to?
So the pole zero excess of t sub c of z has to be bigger than the pole zero excess of g of z. It can't be less. So we couldn't have a pole zero excess of 0 for t sub c of z. What would t sub c of z be with a pole zero excess of 0? It could be a constant. It could have a numerator over denominator where both of those are the same degree or order. Here we need the denominator to be one order higher than the numerator. Restriction 2. So what's restriction 2? Zeros. We're starting upstairs first. Do we need to worry about this one? Not applicable. We didn't have any unstable zero factors in our plant. We had a 0, but it was inside the unit circle. It's at 1/2, so we're okay. We don't need to worry about restriction 2. Boy, he must have failed in designing this problem. There's nothing to do. Restriction 3. What do we need to worry about with restriction 3? Unstable poles. What's the definition of unstable poles is maybe now the question. Outside and or on the unit circle. We can't have something on the unit circle. We want bounded input, bounded output stability. And if you give me a pole or poles on the unit circle, I can give you a bounded input that's going to cause the whole response to blow up, to go unbounded. So you can't have poles on the unit circle. So now restriction 3 is in play. And what do we need to ensure with restriction 3? We could go back to this formula to figure it out, but now we need that 1 minus t sub c of z. We need it to vanish when at the value of z associated with these unstable poles. And we have one such unstable pole, so now we need 1 minus t sub c of z, where? There's where our unstable pole was. It was right on the unit circle at z equal to 1. We need that to vanish. So let's just step through these and then we'll figure out if we can figure out restriction 3. Restriction 4. What was restriction 4? That's steady state accuracy. Did I specify that or request that in the problem? I said I want the system to have a deadbeat response. Didn't say anything about how accurate. So it could go to 5,000 when I hit it with a 1. It's going to go there quick because it's deadbeat, but it may be a bad big error. I didn't say. So this, no error steady state specified. So you don't have to design for it. Let's go back to restriction 3. We need that to be true. And what did we hypothesize for t sub c of z? K over z. We're hoping that gives us enough freedom to satisfy restriction 3. If it doesn't, then we have to make t sub c of z a little bit more complicated. Give us more unknown variables so that it gives us more parameters to play with. We would have to enhance t sub c of z, but in enhancing it, we would always need to make sure that the denominator degree is one more than the numerator degree. T sub c of z is k over z. We now have 1 minus k over, when z is equal to 1, the denominator is 1. We need that to equal 0. Is there a k that makes that true? K equal to 1 will satisfy that. So now we have T sub c of z is 1 over z. And in fact, what do we know about the steady state accuracy? Can we say anything about the steady state accuracy of this closed loop system? If we're talking steady state accuracy, now we're looking for poles where? This is like integrators in the analogs case. Now we're looking for poles at z equal to 1. Do we have any poles at z equal to 1? Open loop poles. Yeah, we had one in G of z in our plant. Our plant actually possessed a pole at z equal to 1. That's going to give us good steady state accuracy due to constant inputs. So in fact, restriction 4, since we had an open loop pole at z equal 1, there will be 0 error due to a constant input, as long as we can keep the closed loop system stable. Is the closed loop system stable? What is governing our closed loop system? T sub c of z, what we're trying to design. Is that guy stable? Are its denominator roots inside the unit circle? One's right at the origin, it's a deadbeat. So yes, it's stable. We can now find c of z. That's 1 over g of z using the formula times T sub c of z over 1 minus T sub c of z. Let's just calculate T sub c of z over 1 minus T sub c of z sort of on the side so that we can plug it in a minute. That's 1 over z. That's our T sub c of z that we just found. 1 minus 1 over z. So T sub c over 1 minus T sub c when we need it is going to be 1 over z minus 1. And now we can use it. Now c of z is 1 over g of z. G of z was this z minus 1 half over z times z minus 1 times T sub c over 1 minus T sub c. The denominator's denominator becomes the numerator, and c of z now becomes z over z minus 1 half. That's our controller based on a Ragazzini design that gives us a desired closed loop transfer function of 1 over z. And now we could look for the answer in the back of the book if we wanted to. You probably wouldn't want to do this on an exam, but at work, you would do this, just to make sure you feel warm and fuzzy going into your boss and saying, here's my controller. Now you say that you have a controller that's whoops, z over z minus 1/2. Your plant was z minus 1/2 over z minus 1. And do you see what's going to happen now in this forward loop? This z minus 1/2 cancels that z minus 1. This z cancels z. And now what do you have really happening in this block diagram? Now it's simplified quite a lot. You now have 1 over z minus 1. It's getting so late I can't even make a summation sign, but here's a minus, plus, here's r, and here's y. We've actually collected a lot of pieces. In fact, in the implementation, here is our input and here is our error. That's nowhere to be found in this simplified block diagram. That's now been consolidated away, in effect. We don't have the input that's going to drive our plant in this block diagram, but this block diagram makes it pretty straightforward to compute T sub c of z. And we know what T sub c of z better be. T sub c of z is now this plant over 1 plus that plant. Yay! Probably don't say that too loud on the exam, because your neighbor might be doing just the opposite and you don't want to really rub it in, huh? But what is your controller? So now you've verified that that controller does produce the desired closed loop behavior that you said you were going to achieve. 1 over z. C of z is right there. It's the transfer function between the air and the input to the plant. So that now, whoops, the output of your controller is the input to the plant, and the input to the controller is the air signal. And that we derived was z over z minus 1/2. And now somebody says, I want to implement this. I want to build this in my Arduino. I want to make this controller happen. Now you have the ability to do that. You can now turn this into a difference equation between your air signal and the input to the plant. Well, let's turn this into delays. So let's now scale this by 1, so that now we have 1 upstairs and we have 1 minus 1/2 z to the minus 1 downstairs. Cross multiplying, we have 1 minus 1/2 z to the minus 1 times u of z is equal to e of z. And you hopefully remember this from previous exams. You now know how to take this into the time domain. Z to the minus 1 is just a unit delay. We now can say that u of n, and I'm going to push that 1/2 to the other side. It's now u of n is 1/2 u of n minus 1 plus e of n. Based on the Ragazzini approach, this would be the controller that would produce that 1 over z closed loop behavior for that plant that we started with. And this one just requires that you store the previous input in a storage location, scale it by 1/2, and add it to the present air signal that you're measuring, and boom, kick that into the plant. Use that to drive the plant. And that's the controller that you would use to create the desired closed loop transfer function. So now the question was, what happens if we actually didn't have an unstable pole? What if this was now something else, z minus 3/4, for example? Then restriction 3 is not in play, is it? So we have restriction 1 met, restriction 2 not applicable, restriction 3 not applicable. This whole exam's not applicable. R4, no air steady state required. What do? Well, maybe now you want to have a DC gain of 1 of T sub C of Z. You could still make that happen. You now are at liberty to basically pick K whatever you want it to be. You could make K be 1/2. You could make K be anything, but you might want it to be something that makes you look better based on the resulting controller. And in this case, you could go ahead and say, oh, let's let K equal 1. It didn't have to satisfy restriction 3, but I kind of like that it gives me a DC gain of 1 for T sub C of Z. That's the first piece. Let's look at some basic root locus patterns. And now we have all sorts of different possibilities. Suppose I give you a pole, and maybe I label it such that this is now your z-plane. What can you tell me about this particular system? 1, can you sketch the root locus? Based on that root locus, can you tell me something about stability bounds for K? Pardon? So now, what's that red line? What's the root locus tell us? The red line or that red branch tells us all the possible closed loop poles for various values of K. Now the question is, can we make sure that for certain values of K, does that red line stay or live inside the unit circle? We're now saying, here's the unit circle. Can I find values of K such that I'm on that red branch inside the unit circle? Do you see that if you crank up the gain to get to that triangle, you would at least start to be stable? And if you kept K less than the K to get you to the box, you would remain stable. So here K is going to live between K, whoops, K box and K triangle. It has to be at least K triangle, and it can't get bigger than K box. This is now the minimum. And you could find that by evaluating the expression for K at z equal to 1. And here is K max. And you would evaluate that when z is equal to minus 1. That's one pattern. Suppose now somebody gives you this pattern. They say, oh, here's one pole and one zero. What's the root locus for that? Do you see how easy this is? Now you can go home and just start playing with your neighbor. Here's a z-plane, here's some x's and o's, sketch the root locus. What's the root locus for this? How many real axis segments are there? 3. How many of those real axis segments are on the root locus? Or which real axis segments belong to the root locus? How many root locus branches are there? How many closed loop poles do you have? How many open loop poles do you have? Unfortunately, if you're listening, you didn't see my finger, huh? So it was 1, 1, and 1. And the root locus, you now step on one of those 3 segments, look to your right, and look for an odd number of poles and zeros to your right, and you're increasing as you move from poles to zeros. The arrow is now pointing to the left. What values of gain K satisfy this system stability? Pardon? All of them, all of the non-negative values of K. K from 0 to infinity stabilizes this system. That's a trivial system, isn't it? So let's look at another one. Suppose now it's like we're playing tic-tac-toe, isn't it? Now we're just placing our x first and see what happens. Suppose we do this. Now what's the root locus look like? How many real line segments do I have? 3. If I'm standing here, I look to my right, I see 1, 0, so I know that this segment belongs to the root locus, and in fact, I'm going this direction as I increase K. What's the range of K for stability? Trick question. I haven't labeled anything, have I? So it's kind of, you need to either ask or label it yourself. So right now you can't say if this is stable or not, or what range of K will produce stability. In this case, do you see that in fact it all gets turned around? If this is plus 1 and this is minus 1, now as you crank up the gain K, you would check for the minimum at what value of z? Negative 1. Now your minimum is negative 1. Your maximum is at 1. Do you see how you kind of have to stay awake during the exam? You can't always assume that z equal to 1, evaluating the K expression, will produce the minimum value of K. Oh, really? Really? Have to worry about which direction these branches are moving. What about this? And let me just go ahead and say this one's at 0.8 and this one's at 0.2. Can you sketch the root locus? And the easy answer is yes. Now you have to do it. But it's similar to what we just... How many branches of the root locus do we have? We actually have two. We have one real line segment, but it possesses two branches of the root locus. One branch begins at point 2 and moves right. The other one begins at point 8 and moves left. And what happens? There's no other poles or zeros. So these meet right halfway between them, and they go off the real line. And halfway between point 2 and point 8, that's a distance of point 6. We split it. Point 3, I can go right point 3 from point 2 or left point 3 from point 8, and I'm at, that's supposed to go straight up, at point 5. One goes here and one goes there, and it doesn't matter. I have some questions asked on the quiz, and one said, if you have two poles on the real axis and no finite zeros, which breakaway line belongs to each pole respectively? I think the question was, is it that? Or does the left one go up and the right one go down? It doesn't matter. So it doesn't matter. It doesn't matter if blue goes right and then down or if blue goes right and then up. It doesn't matter. You don't have to keep track. Once they get together, I don't care which one goes up and which one goes down. Is that clear? Now, are we stable for all values of k? Are we stable for all values of k? If I let k be really, really big, what's going to happen? So now don't forget this guy, your unit circle, right? You can't forget that, because up here and down there, it's the same value of k to get to both places. You now have to find that. Do you know how to find that z triangle? Do you know anything about z delta? You know where it is vertically, right? You're going vertical. At what location? 0.5. So you know that it has a real part of 1/2. What you maybe don't yet know is its y value. But what else do you know? You need to impress your geometry teacher from wherever, middle school or high school, right? Pythagorean Theorem. You know the adjacent side is 1/2. You know the opposite side is y, but how long is the hypotenuse? You're living on that unit circle. It's 1. So you now know that a squared plus b squared equals 1, and a squared, or a, let's say, was the 1/2, and now you can solve for y. And once you have that y, do you know how to find k? We're assuming that the plant, let's say the plant didn't have any gain associated with it. It was just 1 over z minus 0.2, z minus 0.8. Is it clear where that came from? Magnitude condition, kg is equal to 1. If I would have called that g bar, it would have been kg bar, but I just left it as g. So now I know that k is equal to That. And I know the maximum value of K, let's say, is K delta. And I've now solved for y, so that now z delta is 1/2 plus jy. Boy. Still have a couple hours left in me, right? I hope. Who knows if my batteries are still working in my microphone pack. My batteries are always going. I wish. Okay, so do we know how to find K delta? Trying to keep awake here. So the K for stability is bigger than 0. Actually, it's greater than or equal to 0 and less than K delta from that root locus. Let's look at another one. This is getting kind of fun, isn't it? 2 poles and a 0, right? You know this one.
I have a question. Like, for the actual evaluation, finding the max K, like, what is the process there? Like you said, K.
So now for finding the range of K for stability, we look at the minimum value, and sometimes that might be when I first enter the unit circle. Here I'm always in the unit circle to begin with at K equals 0. So now I'm saying, do I ever exit the unit circle? And in fact I do, and I exit at that triangle location. So if I can find the gain at z delta, I know my range of stability. It's from 0 up to K delta.
You have to worry about the other one. Like,
I don't have to worry about the other one. They're twins. So they occur at the same value of K.
oh, because they're both like,
They're symmetric. They're going at exactly the same rate out exiting the real line. What about this bad boy? And I just broke my... Not going to matter if I run out of batteries. It's going to run... Never mind. Let's keep going. How do we sketch this? First, we need to identify the line segments that belong to the root locus. How many branches of the root locus do we have? How many root locus branches do I have? How many real line segments do I have? 4. How many of those are a part of the root locus? I hear a 2, okay. Which real line segments belong to the root locus? To the right of the first x? No. How about between the x's? All right, there's 1. And how many root locus branches live there? How many root locus branches do I have? 2. And where do they begin? At the open loop poles. So I have 1 branch going right. I have 1 branch going left. Is the origin a part of my root locus? No, because I have 2 poles to the right. What about to the left of that 0? How many branches are on that line segment? How many root locus branches are on that line segment? I haven't gotten there yet. Somebody said we got a circle somewhere. We're doing a lot of circles. It's getting late, isn't it? Whew. But we can still have fun. That's relative too, isn't it? We were talking about relatives min and relative max before. How many branches are on that segment to the left of the 0? 2. We have one branch going to the finite zero and one branch marching off to infinity. And now we have to worry about how do we connect those two branches. They can't just magically show up. And that's where and for this pattern, that's where the circle comes in. The circle is centered at the zero. The radius is the geometric mean between those zero and poles. So if I just quickly eyeball it, this is what it is. What's the stability range for K? You can shrug all you want because I haven't labeled anything. But what do you know? Eventually, will this system stay stable, no matter how it's labeled? You can answer that. If I crank up K enough, even if my unit circle is right there, eventually I'm going to go unstable at the gain to get me to that point. Question? If the unit circle was blue, we'd have a problem, huh? We'd never be stable, would we? We would always be outside the unit circle. So depending on whether we're blue or yellow makes a big difference. In the blue unit circle, we have no values of K for stability for this combination of poles and zeros. And do you see how you could modify that unit circle if it was a different color? You could have different possibilities for stability. Oh no, I don't take any more questions now because I'm having too much fun. Let's see what we have there. Well, that's quite a unit circle, isn't it? So before I get to your question, I want to worry about this purple unit circle. What do we have now? Can we even answer? Now we have to have a minimum value, don't we, to get in from the right, and we have a maximum where it's escaping out of the outer piece, or top and bottom. So here we would have a range. We would have some K min and some K max for the purple.
So why is the blue one not outside?
So now the blue circle, the blue unit circle, never has any of the two branches simultaneously inside it. You
Nothing to do with like whether the pole is inside or outside.
what you want for stability is you want simultaneously to have all of your branches at some point inside the unit circle. Whether they begin there or not is not as important as if at some range of K do they get inside that unit circle. So that's what's happening with the purple. What else do we have? We have all sorts of, wow, pages. Let me do one that you haven't seen yet. Suppose I give you the following. Can you now tell me which real line segments belong to the root locus? To the right of the rightmost pole, is that on the root locus? In between the two right, between the left two, to the left of all three. How many branches of the root locus do I have? How many poles did I start with? 3. How many branches do I have? How many branches exist between the two right poles? So I have a branch there and a branch there. How many branches exist to the left of the leftmost pole? Just one. Oh boy, what happens? Well, we'll learn different rules, but essentially now we have to worry about where these, how many branches of the root locus are going to infinity? Eventually, how many are going to, can I just stop between these two on the right, my root locus? No. And now, in fact, what we will learn is that, you know, I wish I could cover up that one on the left. When we just had two poles, they went off at 180 degrees divided by 2. Their fundamental angle was 90 degrees. Right here, this angle was 90 degrees. Down here, we have 3 asymptotes because we have 3 zeros at infinity. We have 3 branches going off to infinity. The base or the fundamental angle will be going at 180 divided by 3, or 60 degrees, and it will be centered, the asymptotes will be centered at something called a centroid. Let's just say that that's the centroid right here, sigma sub a, and this line is supposed to be 60 degrees, and those asymptotes symmetrically divide the entire z-plane. One branch goes off at 180, one goes off at 60. Those two are separated by 120. If I split 360 3 ways, the angle between those asymptotes is going to be 120. So this one is minus 60. And what happens? Well, these two meet, they break away at a relative max. One approaches that asymptote, the other approaches that asymptote, and one goes to minus infinity. So depending on where these poles originate or live relative to the unit circle, eventually they're going to go unstable. Yes? So if that pole to the left wasn't there, you know how they're going to behave, don't you? That third pole, they all are on the same z-plane. They all influence each other. So in this case, the asymptotes are at plus and minus 90 degrees. They're 180 degrees apart. They split 360 in 2. When you had 3 branches, they split 360 3 ways, and the fundamental angle from the real line is 180 divided by 3. Here it's 180 degrees divided by 2, that fundamental angle. That's 90 degrees. Don't worry so much about the 3. The nice thing, though, here is you need to be able to find the real line segments that belong to the root locus and how many branches there are. That's in our first 3 rules, isn't it? And we also know that if we calculated the gain k between those 2 rightmost poles, where do they break away? At what condition? You can't tell me an absolute, but at the relative max between those two, and it may not be exactly halfway between because you've got a third pole that's influencing. So we would have to numerically or graphically determine the maximum relative max between those two poles. Where is that? That's where they break away. If that pole on the left was far away, then it would be pretty close to the midpoint of those two on the right. But if they're 3 together, then they may not quite be meeting exactly in the center of those two. That center meeting is only when you had the 2. I think I've entertained you enough, huh, with 2 poles and a 0, 1 pole and a pole and a 0. Good luck on the exam, and I'll see you exam day.